Welcome guys to week 3, day 2. We're looking at Mr. Shammy's solution to fizzbuzz. And you'll see what he did here was he unrolled a loop. So rather than having a loop going and counting every time and doing a modulus, which is actually fairly slow, if you had to do modulus in assembly, it's like 70 or 80, cycles or something like that. So he did it very cleverly by adding 1 each time, moving it into R0, and printing the number. Now, one thing that he could have done to optimize it was, you see how he adds 1, then he prints fizz, and then he adds 1. Fizz doesn't actually use R4 at all. So this line here could have been, where was I? Commented out, and then just made this an add 2 instead, right? So there's no reason to add 1 each time, and that's the approach that I took. What I did was I had it do it in groups of 15, and so because every 15 numbers it will repeat, right? So what I did was I had it in group of 15, like Mr. Shammy, and then once we got to 90, then I did the last 10. But I did it a little bit more cleverly than him. I actually put the escape in the middle of the 15, and that branched out from there. And so it saved me some more branches. So my total count was 29 or something like that. Yeah, but this here, if you're branching to the next instruction, this isn't C++. In assembly, it will simply go to the next instruction anyway. So I saw a lot of people doing this kind of jazz here, where they're branching to the next instruction. You don't need to do that. Just comment it out. It'll fall through. Assembly just goes down, right? So, and then this technically is going to count against you. So I would delete all that as well, and I would not have the BXLR in there as well. Pop PC will return from the function. Okay. So what Mr. Shammy did here is a technique called loop unrolling. And so because branches can be expensive, if an optimizer knows how many times a loop's going to run, it'll actually replace, for like if you're going to do something like 10 times, it'll actually replace the for loop with just like copying and pasting the code 10 times. It's a very common optimization strategy to cut down on the number of branches you have. And that's why it costed the things that they did. The cost of a branch is actually not 7. It's complicated. And we'll get into a lecture on branch prediction in the future. But the upshot is, in order to avoid if the CPU can guess which way it's going to branch, the cost is minimal. If it guesses wrong, then it has a big penalty, like 7. So use subtract and set and looped. Yeah, that's what I did too. I used subtract and set to avoid a comparison. And then I had my counter counting up like Mr. Shammy did, except I had adding 2 or adding 3 sometimes, if it did like a fizz and a buzz. And that would cut down on some of the things. But basically his approach was the same as mine. My original approach was 70 or 80. That was because I wrote that in the before times and before the coronavirus broke out. And what I did on that one would be similar to what Mr. Dolio did for his assignment, in which he did something like this, right? So he has different counters that count up, and he counts up in R5, he counts up in R6, he counts up in R7, and when it gets to 15, it branches to 15. When it gets to 5, it branches to 5. When it gets to 3, it branches to 3. And so this is actually pretty close to what I did the first time that I did this assignment. And then he prints the number if it's not none of these, and then he'll and then so he'll branch down to 15, and then that resets the counter. If you branch to 5, it resets the counter. And so that approach is how you can do modulus without a modulus. You just have a counter counting up every time. When you hit 15, you're like, all right, print 15. When you hit 5, print 5. When you hit 3, print 3. It's a lot of branching. It's super readable. Yeah, and that's the original way that I wrote it. And my account was like, I don't know, 80, 85 or something like that. And I looked at it, I'm like, no, that's way too many branches. And so I rewrote mine similar to the way that Mr. Chamois did it. And the only difference was I avoided an extra branch by having my escape in the middle of the loop 10 lines down, because you go through the loop of 15, 30, 45, 60, 75, 90, and then 10 down was my escape to the bottom of the loop. And so I didn't have to have that whole copy-pasted section that Chamois did for the last 10 numbers. Instead, I just reused the same code again, and it would jump out after 10 if I had hit 100. So that was my one cleverer thing than what Mr. Chamois did. Can you check to see if I needed all my branches? Yeah, so no, I think my par was 35. Yeah, Hazelton definitely did a better job on that than I did. Become Devello. Oh yeah. So if you guys are getting this that error message, cannot open dev pts 14 permission denied. Edit your cshrc file, vim.cshrc, and delete this line right here. Then when you log in, it doesn't do that. $79 strokes. All right, so top. So you start off by initializing R4 to 0. You add 1 each time. You move R4 into R0. You branch down to check fizzbuzz. Fizzbuzz copies R4 into R5. I don't know, like, you could move this to here so you don't have that branch, right? If you got that branch always there, you might as well put this code up here. Okay, fizzbuzz top, subtract R5 15, and then you branch if you equal, subtract and set. Okay, so he's subtracting 15 from R5. If it hits 0, then he prints fizzbuzz. If it's equal to 0, he branches to continue. If it's greater than, he goes to fizzbuzz top. So there's, yeah. Alright, so he's branching all over the place. So it's going to be sort of painfully expensive to do that. Alright, let's go ahead and grade it. Sudo collect homework. And if people in the future watching this video don't copy it, any of them. I do have copies of everyone's source code. Alright, so 1 out of 1. There's only one test case. Alright. Discord Nitro. Look at Tarangio's thing is next level. Okay. You check if I needed all my branches. Yeah, so a lot of times branches can be eliminated, and because branches can feasibly have a big cost. You know, that is something that optimizers will take a look at. What's called branch prediction has gotten a lot better in recent years. The Intel CPUs in particular have done some really amazing work where they figure out exactly how many times a loop is going to run, and they have like a whole block of silicon just for figuring out, okay, this thing is going to branch this way exactly 100 times, then branch out, and there's a lot of thought that has gone into that. And the reason why branches are expensive, you won't understand until we get into pipelining. But the approach that Mr. Shammy took there, by eliminating as many branches as possible, is exactly what I wanted you guys to do for this assignment. Because by making branches of a cost of 7, you guys were optimizing away the branches, right, as much as possible, and that was deliberate. By changing the costs of these things, if I had made branches a cost of 1, then your fizzbuzz assignments would have looked completely different for the code golf. So because very few people were near par, I'm going to actually have to go through everyone's submissions on Canvas. Make sure you guys on Canvas posted how many strokes your code was. Remember, BL is free if you're doing the function call to the C code. They're not free if you're trying to cheese your way around the branching within the code. It's just the calls to the C code is free. And the B's have a cost of 7. Adds, most normal instructions are a cost of 1, and multiplies are a cost of 4. Okay. Asus and Colorful are shipping the first Intel graphics cards. Yeah, that's it's interesting. I mean, you know, if Intel just has production, that would set them apart from NVIDIA and Asus, right? Or not Asus, AMD, sorry. So Asus and Intel are making new dedicated graphics cards. Not designed to top the performance table. Yeah. Not interested. Alright. Will that card help me figure out convex holes? So I've been talking with Berkeley recently, and they're really cool people. They're really nice and intelligent people, and they've been working with us to try and get a data science program set up here. And so I might do some cloud computing with you guys in this class, and maybe an IS50B as well. So we'll see how that goes. Sister Tiger Lake integrated GPU slapped onto a PCI Express card. Yeah, I don't understand the point of it. I mean, like I said in a previous class, I bought my CPU in part because it's not wasting silicon on a dumb graphics card I'm not going to use, right? Because back in those days, you could actually buy a video card for your PC. I don't understand, dude. Like, I mean, I get cryptocurrency mining is, you know, causing people to buy GPUs or whatever, but and bots are buying them out and reselling them. But, you know, if bots are buying them and reselling them at a higher price, then they should just be charging the higher price. You know what I mean? Like, there's obviously a market inefficiency somewhere going on right now with GPUs. The iGPU in Tiger Lake is a separate die. Oh, interesting. It's a conspiracy to get everyone back using SLI. Yeah, except, you know, the price of a 2080 Ti. Like, when they announced the 30 series, like, the price of my graphics card dropped to like $400 or something. Like, it was just like this giant price drop, and now it's back up. Like, a used one is $650, and that's not even the final purchasing product, right? Buy it now. Let's see. Look at that, $1,200. $1,200 for 2080 Ti, pre-owned. Not even a new one. Not even a new one. What the hell? $1,000 for a used one. Yeah, just because nobody can get any graphics cards right now. It's crazy. So the thing was like down, and like I was gonna sell mine, and yeah, it's like, oh damn, dude, I'm not gonna get much money out of this, and now the price is just sky high. And so if I can actually get a 30 series, I'd actually be able to resell my 2080 Ti at a good price. You're right, you're on Modulus. Okay. 1070 went from 180 to 300. Yeah, it's ridiculous. It's ridiculous right now. How many strokes are UDiv and MLS worth? I don't know. We'll just call them 4, even though that's completely wrong. You can't use ARM64 for this class. It's ARM32. Okay. There is division and modulus in the floating point unit, but like I said, don't use those for this. Don't use those for this. Okay. So let's talk about stuff. So one thing that is nice, if you guys ever find yourselves repeating the same code over and over again in assembly, which you will, because assembly is a very verbose way of coding, right? Like, you know, like with Mr. Shamy's code, add 1 to R4, put R4 into R0, add 1 to R4, put R4 into R0, doing that over and over again, calling the thing over and over again. It's, you know, it makes your assembly code fairly expansive. And so there is a macro functionality, which looks like this. And what that does is it's just a textual replacement. It doesn't make your code any faster, right? Like this would not have saved you guys any strokes. It would just make your code a little bit more readable. And so what we have here is a macro. .macro is a assembler directive. It means the assembler AS is the name of the assembler, which is part of the GNU compiler suite, GNU compiler collection. .macro will, anytime you see my if down here, like that, anytime you see my if, it will replace it with this code. Okay. So anytime my if appears, it replaces it with that code. Okay. So it compares R4 and R5, it moves this, moves that, it moves that. I think there's one more line of code that isn't in this comment here. It doesn't matter. The point is that it will replace that. If you're doing those 4 lines of code over and over again, then you can just set up a macro, and then that will make your code a little bit more readable. Okay. Look at all these repeated calls to the same 4 lines over and over again. Okay. So this code here is going to branch with link to prompt. Prompt would be a C function, right? Assembly makes me thankful for all the tools higher level languages have. Yeah, sure. But there are tools in assembly like this that, you know, can make your life a little bit easier. Okay. Yeah, and push pop. Oh, yeah. Yeah, this is just showing you how to make a function. Okay. So this is an example of a very simple function that takes in 2 parameters, x and y, and returns the result. So global add function, it should be called myAdd. And so at the start of a function, to recap what we talked about last time, we're going to push there's a set of registers you're supposed to save. In this case, we actually could comment out this entire line. Why? Because we're not modifying R4 or through R11. We're not calling any functions that'll modify R4 through R11. This line could actually be left out. And that would actually be a savings in speed, because writing to RAM is, well, it's not expensive in the sense you're going to get a cache miss. Every time you write to memory, you're going to get a cache hit, because you just talk immediately to L1 cache and you get a cache hit. It's almost free, but it's not free. You're still talking about, like, depending on your architecture, again, it depends, but for this class, we're saying it's like 4 cycles. So the amount of time it takes to write to RAM is 4 cycles, and you might be like, well, wait, isn't it 4 cycles per register you write? And it might be. It depends. So one optimization people do sometimes is that they only write the registers they want to save, that they're going to use, in other words. But as it is, for this function, I would optimize this function by commenting these 2 guys out entirely. Okay. because those are all unnecessary reads and writes to RAM. No need, or the cache technically. It's going to hit the cache. Then we do one line of code, add R0, R0, R1, and then we restore the registers that we had saved, and then we restore the link register into the program counter. And this is the most basic way of doing a function in assembly. Okay, you got a little bit of overhead, right? You got a little bit of overhead. This is not free. This is not cheap. So very common optimization that an optimizer will do is it'll look at that and be like, all right, you've got like a lot of overhead for just one little measly line of code. I'm going to inline that. So when you inline something, what the optimizer will do is, rather than, like, let's say, I don't know, we're in the middle down here somewhere, and let's say the optimizer sees you've got a branch with link to add function. Remember that branch with link is a function call, right? Don't use B for this. Use BL. Okay. So branch with link to the function. It'll save the state of the registers that need to be saved into RAM. It'll add X and Y together. It'll return it into R0. Remember, your parameters are passed in R0 and R1. The return value is in R0. And then we restore these registers. And what the optimizer in GCC will do, if you turn the optimizer on, is it will delete this function entirely. It'll actually delete that function entirely and just replace this with add R0, R0, R1. Or if you want to do that, this works as well. If you do the 2-parameter version of add, the first source destination register is the same as the first source register is the same as the destination register. What are the downsides of using inline functions? It can make your code bigger. Right, in this case it won't, because we replaced one line of code with one line of code. Any optimizer worth its salt would just be like, bloop, and just swap it, because there's no reason to do a function call here. But what if we had like, what if we had like, I don't know, what if we had like 6 lines of code? Obviously I'd change it so they do different things. But what if we did 6 lines of code? Well, now you're starting to get into a case where it's like, all right, every time there's that function call, you're going to have 6 lines of code there. And it's actually going to make your assembly code bigger. Okay. And so inlining will speed up your code in the sense that it gets rid of all of these cache hits, all the memory accesses. But it's going to make your code bigger. And so why does that matter? It might not. It might not at all. And in fact, inlining that might just be a win. Just going to call that a win. I call that an absolute win, like the Hulk says. But remember, kids, your level 1 instruction cache has a fairly small size, right? Your level 1 instruction cache might be as small as like, 8K, right? And if your assembly code stops fitting into cache, then you start getting cache misses just from loading the next instruction of the program. Yeah, your performance will tank, right? And so there's this trade-off between your program getting bigger and not maybe fitting into cache, and the cache misses here. And so oftentimes there's no like right answer, right? Like if you are writing it, you can oftentimes make decisions based on what you know better than the optimizer can, because I'm only going to be writing this on, I'm only going to be running the program on this one particular CPU, like you're making an arcade game or something, right? And you know what the CPU is going to be. And I know how big its L1 cache is, and I've written the whole thing, and I know it's right at the limit of the cache size, so I'm not going to inline all of these things, because then the code will become twice as big, it won't fit into cache anymore, and my perf will tank, my performance will tank, right? The optimizer just has to guess, right? A lot of times it's like, I don't know, do you have other .o files? It doesn't really have the sort of comprehensive view of the system that you have sometimes. And so you can give hints in assembly, or sorry, in C or C++, and you can write something like this, or you can write the inline keyword like that. That's valid C. It's valid C++. And what that will do is that will hint to the compiler, hey, bro, you should inline this function. And what's really funny is that it actually doesn't do anything, right, per se. So the optimizer could look at this and be like, yeah, man, I was going to optimize this anyway. It's one line of code. You guys understand? The optimizer could have just been inlining it anyway, and so this thing did nothing in that case. Or it could be such a big function, the optimizer looks at them like, I know you want me to inline that. I'm not going to inline that. That is way too big. And so inline is a hint, though, to the compiler, and the compiler might be more inclined to inline it if you have the inline keyword there, because it'll trust that you know something that it doesn't. And so sometimes putting the keyword in there will decrease your performance, and sometimes it will increase your performance. And so when, that's one of the things we're talking about in this class. You guys are old enough now to know how computer, optimizers work. And the reality of this situation is it's a messy topic, right? Like it's, you ask questions online like, what's going to be faster? Will it be faster if I put inline here or not? And the answer is run it, benchmark it, find out. In the case of this function, this specific function here, it'll probably do nothing because the optimizer would undoubtedly have been inlining that anyway. There's no reason why an optimizer would not be inlining that function. And again, inlining just means, see how there's no function call, right? It gets rid of the BL, it gets rid of all the pushes and pops, gets rid of all that, it just puts the meat of the function into wherever the function was called. Okay. So, one thing you'll hear from experienced people over and over again is, I don't know, dude, try it and find out. Learn how to benchmark your code, learn how to test your code to see if it's fast or not. Okay. And there's lots of performance tools and things like that. And unfortunately with you guys, with your group, we did not do the hash table assignment last semester like I normally do in discrete math, where you guys get experience benchmarking code and things like that. So we might have to do one of those in this class. Where does assembly code come from? Does the code stork deliver it? Yeah, I wish. The push and pop have to be done for every function, correct? Kind of. If it, that's where I start with, and then after I finish my code, I look at it and I'm like, and do you see how I broke these out into two different lines? The reason for that is because if I look at my function and I'm not actually doing anything with R4 to R11, there is no reason to save it to RAM and then reload it from RAM. There's no reason to do that. So if I commented out this code right here, it would work correctly. It would work exactly the same as if it was not commented out. But this is how I start my functions. I just start off saving all the registers to be safe. And because you should always start safe and slow, right? Safe and slow. And then after you get the code working, then you start tweaking it, right? And that's hopefully what you guys have been doing. We've done 2 code golf assignments so far, right? So hopefully you guys have written it once and get it working, and then you start tweaking, you start optimizing, you start cutting it down, you start looking at different tricks and things like that. That's, it's 4th semester. You guys can start really thinking about performance now. In CSci 40 and CSci 41, I turn on address sanitizer, I turn on the safe C++ library, I turn on debugging, I turn on every warning, I turn on all, like, I run CPP check on your code, I run easy peasy on your code. There's like 5 layers of safety on your code. Like, our code is basically Java, right? By the point that you guys are running Hello World, without you even knowing it, I've got 5 different levels of safety on there. Okay, and you don't have those safety nets here in assembly. Your code will just straight up seg fault, which I'm sure a lot of you guys did, right, on the fizzbuzz assignment. Like, you're probably seg faulting at some point. So when a C++ file and a compiler like each other very much, that's funny. Is there a reason to do R4 to R11? We could just push pop R4 if all we use is R4. Yes, exactly. That's what I'm saying. Like, after, like, I start off just saving all the registers that need to be saved. Technically, R11 what's the scratch register? 12 or 11, either way. I save those, and then after I write my function, then I'll come back in here and look at which ones I'm actually using in here. If the only one I used, like Mr. Hazelton said, is R4, then I would only push R4. I would only push R4, and I'd only pop R4 if I was using R4 in the function. And this is actually this is an optimization the optimizer will do. The optimizer will do that optimization to avoid unnecessary reads and writes. Yeah, it is basically Java. Like, because every time you access memory in Java, the Java virtual machine will do bounds checking on it. It'll be like, is that within the array? You know, you're iterating through an array. If you go outside of the boundary of an array in Java, it will throw an out of bounds exception. And that's basically how I have it set up for you guys in CSI 40, CSI 41, CSI 26. Like, you guys don't even know it. It's just behind the scenes. It's running slowly and safely because you guys need to find your mistakes. In assembly, the training wheels come off, and it's like, you're going to segfault or you're going to segfault. Yeah. So, that's what makes assembly code difficult, I guess. It's not really difficult. Like, there's only, like, however many commands we've learned. Like, it's not really difficult. But it's not easy to debug. Is the fizzbuzz grader case sensitive? Probably. Yeah, if you guys got a 0 because you didn't. How did you not be case sensitive though? Because you should be calling the print functions. It should be. You shouldn't have any control over the output. How do you check your mail on the server? Alpine, maybe? I don't know if I have it installed. Every time I become somebody, I'm deleting these things. Let's see if Alpine's installed in here. Yep. So Rivera got 1 out of 1. Okay, good. I have a lot of aliases set up. All right. Yeah, Alpine will allow you to check your score immediately. Okay, so. Any more questions about functions? Because that's basically the long and the short of it. Begin with the pushes, end with the pops, and then optimize later if you want. With branches, let's talk a little bit more with branches because this is doing some interesting stuff. So with the branches, it reads, okay, so this prints, please enter a number. It reads an integer, it moves the result from that into R4, and it moves the result of that into R7. It reads another integer, saves that into R5 and R8, reads another integer, saves that into R6. It is then going to fix this comment down here. So it's going to call a function called signCompare. Oh no, yeah, it calls a function called signCompare, and then moves the results of that into different registers, and compares R4 and R5. If the result is less than, then it branches to a function called less than. It then runs the if statement again, and then branches if the result was equal into equal to. Runs the comparison again. If the result was greater than, it branches to greater than. So it just prints to the screen, you know. So if you type in 5 and 4, it'll print 5 is greater than 4. Now, if you want, these comparisons by default assume that the registers are unsigned. Okay. So by default, if you do a comparison between two integers, it will assume the numbers are unsigned. If you want to do a signed comparison, like a regular int, then you use this. And that looks kind of weird, and it's branch with link if carry is clear. And so there's a carry bit. So if you add two numbers together, you know how you like carry the one, you know, or whatever, you're doing arithmetic. So there's a branch, you know, like greater than, less than, whatever, that says if the carry bit was not set. In this case, it has nothing to do with carry. It's just a signed less than. Sorry, unsigned. Sorry, I said that completely backwards. By default, the comparisons are signed, and if you want to do unsigned comparisons, then you use I'm sorry. By default, branch with equal, less than, greater than is signed. If you want to do unsigned comparisons, you use branch with link carry clear. Equal is the same because the bits are the same, and branch with link carry set. Carry set means greater than. Carry clear means unsigned less than. Okay. Unsigned means it has to be positive. Yeah. So for a normal integer, they range from negative 2 billion-ish to positive 2 billion and change. For an unsigned integer, that means it ranges from 0 to 4 billion. And so we use unsigned integers really not for the purpose that you think that we use it for. A lot of people will use unsigned integers just because they're like, all right, we're doing a bank account balance, and your bank account balance shouldn't be negative, so we're going to use an unsigned integer to represent your bank account balance. And then their code explodes when somebody, if you're trying to do a transaction, so you got $10 in the bank, they try to ring you up for $100. You subtract 100 from 10 to see if you have enough money in there, and then because the result can't be negative, it becomes 4 billion. You're like, yeah. And so just things explode. Usually in those situations, you just use signed integers. The reason why we use unsigned integers is because it allows you to do one comparison instead of two. Okay. So let me show you what I mean. Let me hop back into C++ world for a second. So let's say int r just so you guys might have seen this type before in C++ called size_t. It's basically an unsigned integer, but the size of it actually depends on the size of your memory. And so on systems that have more memory that's accessible, like on a 64-bit system, you have more RAM that is accessible than on a 32-bit system. Size t would be bigger. So size t kind of changes depending on your architecture so that you can access kind of any part of RAM. But it's an unsigned integer. And the reason for that is because, let's see here, so we're going to initialize, so this would initialize the array to be all zeros. Did you guys know that? Like, you can zero fill an entire array by using curly braces. But I'm actually going to, this is basically iota. There's a standard library function called iota that will fill arrays and things like that with 0, 1, 2, 3, 4, 5, so on and so forth. So array element 5 will be set to 5. Array element 9 will be set to 9. What element do you wish to read? Now, actually, let's do it the bad way first. Okay. So we're going to read a number from the keyboard, and now we need to bounds check, right? We need to bounds check to see if, if they type in 5, we'll print out element 5. If they type in 9, we'll print out element 9. But if they type in a negative number or they type in 1,000,000 or whatever, then we have to say, sorry, that's out of bounds. Okay. So, come back. Now we're doing C++. Did you go to Taco Bell or something? Last year when I taught this class, Nate Beal was like, in the Taco Bell drive-thru, I was like calling on him. He's like, hey, I'm ordering a bean burrito right now. Online education, right? So if we want to bounds check an int, we would have to do something like this. If element is less than 0 or element is greater than or equal to size, cout out of bounds. Okay. You guys understand? Pretty shouldn't use an int for Elon Musk either, yeah, because his bank account balance, well, his net worth is over 4 billion, right? So, by the way, this is just as an aside. When somebody is worth $400 billion, that does not mean their checking account has $400 billion in it. All of Elon's money, more or less, is tied up in Tesla. Tesla's stock has been going bananas. He owns a lot of Tesla stock, so he's worth a lot of money. That doesn't mean that he could pay somebody $400 billion in money. And that's something my friends on Facebook who post all these memes, like, look, nobody needs more than $1 billion. Let's take away, all their wealth above $1 billion. It's like, that's not cash, right? Like, they don't just have 400 billion in cash. Like, nobody has 400 billion in cash sitting around. What they have is stock. And so if you're going to take away all of his wealth above $1 billion, what you're doing is taking away his company from him, right? Which is a very different, thing, right? Sorry, you can't own the company you started anymore. We're now the majority owner. It's called communism, right? So, Dr. Zhivago, nobody needs a house this big. So we moved in 8 families with you. Okay. Anyway. So this is 2 if statements, right? And so this is going to involve a comparison, and then if it's less than a branch, like greater than a branch, something like that, right? And greater than, and so it's going to have a couple different branches in there, and it's going to be more complicated, right? Like, as you guys saw, there's going to be some different jumps and things like that in there, and that could be expensive, right? So it'd be a lot better if we could just do this, right? Wouldn't that be nice? You guys with me? You can't do that with an int. Can't do that with an int. That's why unsigned int exists. That's why unsigned int exists. If they type in a negative number, it wraps around, it underflows, and it becomes, 4 billion or whatever. And so with an unsigned integer, a lot of times you only need 1 comparison instead of 2 comparisons. That's why unsigned integer exists. Okay, it's not because you don't want to represent a bank account with an unsigned integer. It's a dumb idea, because anytime you do subtractions and you accidentally go negative, it'll wrap around and your balance is now $4 billion, right? And the Java got rid of unsigned integers because they don't care about speed, right? Speed is not one of their priorities. Safety is their priority, and so they got rid of unsigned integer because they're like, just do both comparisons. We don't care about it being fast. So they got rid of it because a lot of people would mistakenly subtract 10 minus 100, and if that's an unsigned integer, that underflows. Right? So Gandhi, right? So Gandhi's aggression was stored in an unsigned char. So Gandhi's aggression was set at 1 out of 10, and if you build the United Nations, it lowers everyone's aggression by 2. And so Gandhi's aggression level would underflow from 1 to 255, and Gandhi would become 25 times more aggressive than the most aggressive AIs in the game, and start doing nothing but building nuclear weapons and nuking the crap out of everybody, right? So this is in Civ 1. Yeah, it's one of the most famous bugs of all time, right? Is the Gandhi, nuclear Gandhi is what it's called. And so when Gandhi's granddaughter came to our campus last year, I got a photo with her. And I was going to, right, yeah. I was going to ask her what she thought about the nuclear Gandhi meme. But she there you go. There's nuclear Gandhi. But she seemed like a very sincere person, and the previous person in front of me in line asked her a question, like, you know, what could we do to make the world a better place? And she took it very seriously and answered it for about half an hour as I was standing there in line, and I was just like, all right, I don't want her answering kind of a joke question for half an hour. You know, I feel kind of bad about it. You know, so I just went up there and took a photo with her. I was a good person, you know. So, but yeah, so nuclear Gandhi was the result of people using an unsigned integer, or an unsigned char in that case, and it underflowed. And so in Java, they just got rid of it for those reasons, you know. And in C++, a lot of problems are caused by using unsigned, because it's you can accidentally wrap around to 4 billion easily. Okay, but do you guys see why? You guys see why? If you do 10 minus 90 and unsigned, you will get 4.2 billion and change. And so if the user types in -1 here, -1 becomes 4.2 billion and change. 4.2 billion and change is bigger than size. It will print out of bands. Out of bands. Out of bands. The battle of the bands. Amazing. That's why you shouldn't type and talk at the same time. Out of bounds. There we go. Okay. So, and these things make more sense after you've had this class, right? Like, this is why I had you guys optimizing fizzbuzz and getting rid of excess branches and things like that. Because now it's like, oh yeah, that language decision that C++ made makes sense now, because branches kind of suck, or they might suck, you know? And so if you can do something that'll just give you a free, you know, a free if statement, eliminate a free if statement, then cool, you know, right? So this class kind of makes C++ make more sense, right? And then you look at Java and you're like, okay, well, that also kind of makes sense, because Java doesn't, you know, really care as much about being fast. Could you go over the CC and CS suffixes again? Sure. So the CS and CC suffixes is, which one was it? Functions. Unsigned integer. So if you want to do an unsigned less than, it's CC. If you want to do an unsigned greater than, it's CS. So if your variable is an unsigned integer, you use CC and CS to do less than and greater than. Okay? And if you do assigned arithmetic, and I apologize again, I said it backwards originally. LT is signed comparison. So if you have int x, y, you just have an int. If you just have int, you use the regular less than, equal to, and greater than comparisons. Okay. These are used if x and y are unsigned integers. Okay. And the reason why they're different, well, we have to learn 2's complement first, and we haven't done that yet. Counter-strike comparison. And you do that after a comparison, yeah. So myIf has a comparison in it. So every time you see myIf, it's doing these 4 lines of code. So myIf is a macro that I set up. Again, if you want to have a macro, you just say .macro, you give it a name, and the assembler will come in and copy-paste these 4 lines every time the word myIf appears. And then it ends with the .end macro directive. Assembly directive. Okay. So we got myIf, and then down here we got unsigned comparisons. And now we've got greater than or equal to. And yeah, okay. Any other questions about that? Well, you lose your comparison when you myIf. Well, myIf has a comparison in it, right? So every time you do a myIf, it does a comparison. And so that clears all of your previous comparisons, right? So, yeah, but what it's doing is doing the comparison, and then it's moving the values into these parameters here. So the functions that I keep calling all take 3 parameters. And so the first parameter is R0, second one is R1, third one is R2. And so rather than typing move these things over and over again, I just wrote a macro to do that. And it makes the code a lot more compact. Yep. But there is a comparison hidden in there, so yeah. And remember, every time you do a function call, your comparisons are probably going to be toast, right? Because almost every function you're going to call is going to do a comparison at some point within it. And it'll erase whatever is in the secret CPSR, status register. All right, so let's look at loops real fast. So here is some C++. All right, this is going to be powers of 2, right? So 5 times it is going to multiply x by 2. So it's going to go 2, 4, 8, 16, 32. Okay. So whatever y is, it's computing 2 to the power of y, right? Okay. All right. So let's do a loop. So here's what loops look like. So it puts 1 into x, it puts 5 into y. That's our remember when you do multiplication, you can't use the flexible second parameter. Most commands in ARM32 have a flexible second parameter. Multiply does not. Multiply is much more restrictive. So if you want to multiply by 2, you have to put 2 into register and then multiply. So look, I'm doing the subtract and set trick, right? So it's usually better to count down, and then when you hit 0, bail out. And whether or not it's branch if less than or branch if less than or equal to depends on if you have that at the top of the loop or the bottom of the loop. Okay. If it's at the bottom of the loop, it would be less than or equal to. If it's at the top of the loop, it would be less than, because there's one extra, do one extra iteration. So just as a rule of thumb for you guys. If you're doing the subtract and set at the top, it's probably going to be less than. If you're doing it at the bottom, it's going to be less than or equal to. Or just don't worry about it, and you will see that you're off by 1, and then change it. Right? That's the standard assembly programming way of doing it. I'm going to run it and count how many times it runs. Okay, it ran 5 times instead of 6. Okay, I need to change that to a less than or equal to, or something like that. Right? Or just change the number, add 1 to y or something. It's the because we don't have that nice for loop. We got to write it yourself, right? And that's why when I teach for loops in C-Sci 40, it's for int I equals 0, I is less than blah, I plus plus. That code will run exactly blah times. And in assembly, it's like, now you got to start thinking about it, like, okay, all right, first time through the loop, it goes from 5 to 4, and it does the subtract and set, so 4 is greater than 0, so it's not less than. You start seeing they're counting on your fingers and toes, and you're like, okay, I think that's right, and you run it, you're off by 1. Off by 1 errors are very common. It's one of the most common types of bugs. But just as a general rule of thumb, if you guys care about it, is when you do this trick, if you want the loop to run 5 times, which is what you normally do, right? You put into register 5, or whatever register you're using, how many times you want your loop to run. If you do this at the top, it's going to be less than. If you do it at the bottom, it's going to be less than or equal to. Okay. Because it'll do one extra, chunk of the code. It depends if you're doing a while loop or a do while loop. A do while loop runs once, always, and then does the comparison. A while loop might not run at all. That's the only difference. If you put this at the top, it's a while loop. If you put it at the bottom, it's a do while loop. Okay, and then we multiply R4 by 6 and save the result into R4. We jump back up to the top. We subtract 1 again, compare, and see that does a free comparison to see if R5 is at 0. It is not. We multiply by 2 again. We jump up to the top, subtract 1 again, multiply by 2. 5 times later, it is less than 0, and so it will branch to done, and it will put the value of R4 into R0 and quit. So this will compute a power of 2. I look away, I look back, I see C++ and ARM on the same screen. Yeah. I mean, there's a lot of that, right? So you can see it computes 32. Is there an add-in set? Yeah. You can add the S suffix to almost everything. You can't add it to like directives and things like that. Pretty sure there's like some instruction you can't add it to. I think you can't add it to a comparison. That'd be really weird. Compare and set. I don't think that. I don't think you can do a compare and set. Let's find out. Nah. Oh, it's deprecated. You can actually do it. That's hilarious. You can actually do it. It's deprecated. Please don't use it. That's a dumb idea. So, page 90 in the Bruce Smith book has a really good table. Yeah, the Bruce Smith book is really good. It's a really good book, and it's not $500. If it was a textbook, it would be $500. But because it's just some rugby player writing books about assembly in the mid-country, the Midlands of England somewhere, I don't know where he's from actually. That's just my mental headcanon. Bruce Smith, ARM 32. His website's pretty good too. When it's working, he died. Oh no, different guy. Yeah, I thought he had died because his website hadn't updated in a while, and but his website's actually got some good references on it as well. Sports books, let's see. Cricket, Arsenal, yeah. About Bruce Smith. Let's see where this guy lives. He programmed on the Acorn. So the Brits had a computer called the Acorn, which is like the Apple II for the. I don't know if you guys know what an Apple II is anymore, but it was like a computer made for kids, kind of. And so a lot of British kids in the 80s grew up programming on the Acorn computers, and that became ARM, right? ARM. A stood for Acorn, Acorn RISC machines, and since then they've just become officially ARM. But originally it stood for Acorn, which is like it's really beginner company. No, not Elon Musk. Eben Upton, the guy who created the Raspberry Pi, he got the job that he got by recreating an Acorn computer. He built on a breadboard he rebuilt one from scratch and using modern technology, and so that got him his job at ARM, I believe. I believe he worked for ARM, yeah. And when he was at ARM, he proposed the notion of a cheap $35 computer that you could give to kids, basically. I mean, hell, the Raspberry Pi Zero, which sold for $5, they included that in a magazine. Like, you buy a magazine, the Raspberry Pi magazine, comes with a free computer that can run Linux and a web server and everything. Like it's mind-blowing that even Upton, was able to pull that whole thing off. And yeah, and his love for cheap computers that kids could use and learn to program on and stuff like that. Because what happens if a kid steps on it, right? You buy another magazine, right? You go to the 7-Eleven and buy another magazine that comes with a free computer, So the magazine immediately sold out, right? And so Raspberry Pi Zeros are actually oftentimes hard to find. But literally it was a $5 computer, All right, so BBC Micro, yeah, plays football, soccer, as we call it here. Stadium Arena Management, magazine for managing soccer. He designed the waste infrastructure at Arsenal's Emirates Stadium. Yeah. Currently living in Sydney. Okay, so sorry, he's not living in the Midlands. I just made that up. He's living in Sydney. Okay. But I really like his books, and he just looks like a nice dude. I don't know. I've never met him, but he just seems like a really cool dude. I don't know. And his books are amazing, and they're cheap, and they're really well made. I wouldn't recommend. I've got over here. I've got numerous other assembly books. This one's okay. Let's see here. This one's called Assembly Language Using the Raspberry Pi. The bridge between hardware and software. You see that? There's a bridge there by Robert Dunn, I believe. Yeah. And it's got lots of programs and things like that. I think if you want, it's a good second book. That one. It's Dunn, D-U-N-N-E. And if you want a second book on assembly programming, it's good also because it talks about different things. It's got lots of programs in there, so you can learn how to do more stuff. But I would definitely start by, I would honestly just start by reading Bruce Smith's book from cover to cover, honestly. Okay, so any questions about loops? I mean, none of this stuff is really hard, I would say. The table I was talking about is in the Third Ed Raspberry Pi book, which I own a couple of those. I don't know where they are right now. Any questions about loops and functions? Some people mailed me before this class, like, how does this class compare with CSI 40? And I don't know, like, in some respects, like, it's a lot easier, right? Like, you're learning a new language, but it's not, I don't know, it's not really that complicated. You have a lot less support. Right? In C++, you just see out things, whatever. You have address sanitizer telling you if you go out of bounds, and ubisan telling you if you underflowed or overflowed. And assembly, it's like, welcome to the big leagues, kid. Don't segfault. New language, same old concepts, at least so far. Yeah, that's a good way of putting it. And it's not, I don't know, it's not bad. Your basic tools in assembly are fairly small. Having an easier time because of understanding concepts. Yeah, if you know how to program, then I don't know. I found that assembly is pretty easy to pick up. All right, so let's talk about ands and ors and nots. Let's see here. When do we do ands and ors and nots? Shift pointers. Do I not have anything on and, ors, and nots? That's shifting. Huh. No, I don't. Okay, well, I'm gonna have to make one for you guys then. Or I'll just add it to logic right now. Okay. So, oh, there it is. And okay, yeah, okay. It is in there. It's just commented out. All right. Okay, so. So if you want to have a more complicated if statement, and this is what your next homework assignment is going to be, you're going to be doing code golf with assembly if statements, and so you're going to have complicated if statements basically. All right. So here we've got a standard and from C or C++. X is equal to 42, y is equal to 21. If x, and for those of you that aren't familiar with C++ as much. When you say if x, that means if x is not equal to 0. In C and C++, 0 is false. Everything else, -1, +1, 100, -100, a million, a billion, -a billion, are all true. So in this case, it's saying if x is true, which means if x is not equal to 0, and y is true, y is not equal to 0, then print Coolio. So in this case, it will print Coolio because both x and y are not 0. Okay. If you want to have a more complicated if statement, do this assignment. The books are peak. Google Foo hasn't helped with ARM. Yeah. That was something that kind of shocked me a little bit. Was just how bad the online documentation is for ARM32. ARM actually has pretty. It's got a pretty good. I wouldn't say good. What's the right way of putting it? ARM32 reference. It's got it's got a giant website that has developers resources and things like that in it. And if you want to, read about, stuff, load store timings. Store is always one cycle. That's because load always blocks at least 2 cycles for the load and 3 cycles for the pipeline reload. So it takes at least 5 cycles to do a load. Yeah, so it's got like a pretty good, it takes 3 cycles. And do you guys see how like they use the terminology that I've been trying to instill in you in this class? 3 cycles, 4 cycles. They've got a lot of stuff in here. The trouble is, back to search. They don't explain it very well, and they don't have very many examples, right? So let's say let's look at mul, all right? So here's the documentation for multiply. Cool. That has no mul on it. What happened here? Arm and thumb instructions. Flexi second operand. They got a, so it can either be a constant or register with an optional shift. Let's see, multiply instructions. Here we go. So let's click on mul. I don't know why that didn't come up from the search. So, it gives you the syntax of it. Destination register, source register, second source register, and explains destination register, source registers. S is an optional suffix. Condition is greater than or less than or something like that. So it breaks down the grammar for you. Usage, it multiplies them. That's actually one interesting. The destination register and the source register had to be different in earlier versions of ARM, and so I still avoid sometimes doing that, but on the Raspberry Pi it'll work fine. You could say R4, 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 and that's fine. And so here's your example, right? Like, and this is kind of what I was getting at, is that like their examples are fairly minimal, right? Like, cool, thanks, cool. So it's really not designed for beginners, right? They've got pretty extensive documentation on the ARM developer site, and I don't really want to knock it too much because I use it all the time, and for me it works pretty well. But for people learning assembly, yeah. If you don't know what's going on, you're not going to know what's going on from reading the web pages there. On the worksheet, L1, when you LDR something you haven't stored, is it just accessing RAM? Yes, it is. We'll get to that in a second. I want to get you guys going on the next homework though. So this is going to put 42 into R0. It's going to put 21 into R1, and then what you can do is, so AND is bitwise and that's usually not what you want. You usually don't want to bitwise and something when you're doing and so this is something that a lot of students mess up on. They think that and in assembly is that and. It's not the double ampersand, it's a single ampersand. So what's the difference? So the logical and means if it's not 0. And so the actual answer down here is to compare R0 with 0. If it's not equal, bail out. If compare Y with 0. If it's not equal to 0, bail out. And it prints, returns, something different. And then otherwise it falls through and returns 1. This is actually, do you guys understand? Like, compare X with 0. If it's not equal to 0, bail out. And so I'll talk about short circuit, what that means in a second, but basically it's going to say, is it not equal to 0? Is that not equal to 0? Okay. And if they're both not equal to 0, then it calls Coolio. Otherwise, it calls not Coolio. It's 2 separate compares. Okay. The AND, this is a way that a lot of students try and do it. And what they're doing is this is a bitwise AND. It's a bitwise AND, which means switch into programmer mode. Show me the bits. All right, so that's 42, right? Lol, lol, lol. 101010. It's 42, right? And so if you were to bitwise AND this with 21, 21 is 10101. It's 42 right shifted one time. All the let me just write it down here. So X is 101010. Y is 010101. Like that. So if you bitwise AND them, what happens is the CPU will go through every matching pair of bits in the numbers. So 1 ANDed with 0 is 0. 0 ANDed with 1 is 1. 1 ANDed with 0 is 0. 0 ANDed with 1 is 1. And it will give you false. It will give you 0 as a result. Now, a lot of times you might happen to just get lucky, right? Like if Y was like some other number, like 22, it would return true, and you'd be like, cool, my thing works. No. You just got lucky that the bits worked out the way they worked out. So you don't use AND or ORR, and don't use EOR, unless that's exactly what you're trying to do. You're trying to do a bitwise operation. And so so X and X ANDed with Y is 0, 0, 0, 0, 0, 0. Okay. All right. So when you do the AND, you will be horribly surprised sometimes. Okay. If you think you're doing logical AND. Do you guys understand the difference between a logical AND, this one, and a bitwise AND? Are you guys cool with that? Dolio says, I tried doing modulo using bitwise AND. Yeah. And so a lot of hash tables will actually be power of 2 size, because it's very easy to hash an integer into the hash table. You just bitwise AND it with, like let's say your hash table is of size 16. You bitwise AND it with zeros and then 1111, and then it'll hash into one of the buckets. It's a lot faster than doing modulus. And so some of the fastest hash tables out there have a requirement that they're a power of 2 for that reason, because modulus kind of sucks, right? On a Raspberry Pi, modulus might be 80 cycles, right? And so if you can just use AND to just cut off all the upper bits and just take the lower bits, then you can do a very fast hash using that. It's a classic trick, and and people write that in C++, right? So 45, very useful class, very useful class. 36 ANDed with 15 return 4. Yeah, that's used in hashing. That's used in hashing a lot. Okay, so all right. So there's and then there's bitwise options and or I don't like having double comments on a line. Ordered with mine. Eeyore. Sounds like Winnie the Pooh's friend, right? X is equal to X, not exponentiation. Exclusive or with Y. Yeah. Okay. So be careful using these, because a lot of students think they are the logical versions, not the bitwise operations. Okay. So they do work. They do work. Like if you know that x and y are just going to be 1 or 0, then these work fine. Okay. So the bitwise operations can be used if you know that x and y or whatever are going to be either 0 or 1. Then they work exactly the same as the logical. Okay. But the logical and is usually 2 different comparisons. Okay. And what's the difference between single and double and? That's what I just talked about. So the single and is a bitwise operation, so it does this. So it goes through every pair of bits. So the lowest bit gets ANDed together, the next lowest bit gets ANDed together, the next lowest bit gets ANDed together. Whereas with logical AND, it just means if they're both not 0. And so it doesn't do any bitwise comparisons between the two of them. The logical AND is what we normally use in C++. There are times where we use bitwise operations in C++. But normally we use logical AND. And so that's just 2 comparisons. Okay, and so what does short circuit evaluation mean? Well, as it turns out, the way that C++ works, and this is a very nice optimization that is guaranteed. It's part of the language, actually. It's defined in the C language, I believe. So it's not even like part of the optimizer. It's a optimization baked in to the language. If x is false, it will not evaluate y. Short circuit evaluation. Short circuit evaluation. If x is false, it will not look at y. Okay? And so this is oftentimes used in situations like this. So int pointer equals new int 100 if pointer and pointer, let's say we have some code in here. So this is very commonly seen. And so what that's saying is if pointer is not null, null is 0, 0 is false. Okay? So when you new something, or if you do malloc, malloc is the C version of new, it'll return a pointer, which is just the start of memory for this array. So there's 400 bytes of memory here, and it's going to return a pointer to the beginning of it. If the allocation fails, it'll return a null pointer, or in C++ it can throw, depending on how you have it set up. So let's say it returns a null pointer. So it's very common to do something like this, which is saying if the pointer is not null, because you'll segfault if it's null, then it'll check to see if pointer square bracket 0 is 42. You will see this construction all the time in C and C++, which both checks for a null pointer and uses the pointer at the same time. And this will not segfault. Like you would think this would segfault, right? If pointer was null, you would think this would segfault because you're accessing memory 0. It doesn't. Short circuit evaluation says if the first thing is false, if pointer is null, then it does not look at the second part. Okay? It will not access that spot in memory. It will not look at y. And that can be useful. Like you could do, or you can do something like this. If pointer and foo pointer. And so let's say foo is a function that takes a pointer and returns true or false. This will say if the pointer is null, don't call the function at all. That function won't even be called. If pointer is a null pointer, it will not call that function. It'll just skip. So that's a very common optimization technique. I don't know what EOR is. EOR is the exclusive OR. And so there is no logical and, just do a double compare. Yeah. EOR is the donkey, yeah. All right, so what is EOR? Let's see if I can pull up a bitwise operation calculator online. It'll be easier to show it this way. So exclusive OR, the normal thing that we call OR is inclusive OR. If either X or Y is true or both, then do the thing, right? Dahlberg, you familiar with that? Like your regular OR statement. If either X or Y is true or both of them are true, then do the thing. That's actually not what we usually do when we're doing English. The hell? Okay. So let's not use numbers that look like binary. 16 and 18. Okay. So if you can you show the bits for me? Can you show the bits? No. Binary. Yeah. Okay, so 16 ANDed with 18 is 16, right? Because the 2's bit, that's not useful. I actually want to show the bits. Okay, let's try this. 16 ANDed with 18. Can you show the bits to me? Nope, you're not going to show the bits to me either. Oh my gosh.
Use the Windows programmer calculator.
But I want to show both of them at the same time. I mean, I could pull up, OneNote again, but I'm just hoping that one of these guys will show me. No. Just show me the bits, dude. Try option number 4. Let's see if we get another pop-up about cookies or some garbage like that. All right, good. Nope, 1 and... this is binary only. Okay, so 9 and 10, we're going to AND them together. We get, 9 ANDed with 10 is 8. Do you guys see that? For AND. Because 1, the last bit, ANDed with 0 is 0. 0 ANDed with 1 is 0. 0 ANDed with 0 is 0. And 1 ANDed with 1 is 1. Okay, now EOR, exclusive OR, is what we usually mean by OR in English. Would you like to go to ice skating, or would you like to go to the movies? We usually don't let people say yes. When we offer people options in English, we stress the or somewhat. We say, would you like to get pizza or ice cream? When you stress it, it means exclusive or, which means you get to pick one or the other, but not both. And so in this case, it's an or, right? For all the bits except the high one, it works just like or. True ORed with false is true. False ORed with true is true. Remember, you're doing each pair of bits. Each matching pair of bits and the numbers get ORed together. But if they're both true, that's where it's different. That's where it's different from a regular OR. If they're both true, nope, you can't get both pizza and ice cream, and the result is false. Okay, so exclusive OR means one or the other is true, but not both. One or the other of the bits is true, but not both of them. If both of them are true, it's false. One or the other, exactly.
It also show what happens when you XOR something with itself.
Yeah, and so XOR is very useful. So for example, we got 0011. If we XOR this a second time, we'll get the original number back. So it's used in cryptography. If you have a random string of 1s and 0s and you XOR it, you'll get an encrypted message. And then if you XOR it with the same string again, you get the original message back. So here we got 1001, and we XOR it with 1010. We get 0011. Now if we take 0011 and put it here, we'll get 1011. See, we get the original result back. XOR is a reversible operation. So one way you can think of it is every 1 you see down here, every 1 flips the bit. It flips the bit associated with it. So that one there, the second one turns into a 0, and then this one flips the bit here, so that turns into a 1. And the zeros leave the bits, the original bits there. A 1 flips the bit. That's another way you can think of XOR. And so, and it's reversible. And or are destructive. You can't get the original bits back. XOR is reversible. and so it's used a lot in cryptography. You XOR it with a pattern of random ones and zeros, and you actually have unbreakable encryption. It's called a one-time key. Okay, so short circuit evaluation is a way of guaranteeing this will not get called unless pointer is not null. Are you guys with me on this? So if pointer is false, it will not do the second comparison. Yeah. And then short circuit evaluation also works for ORs. So if a ORed with B, call Coolio, that's interesting that syntax highlighting turned off halfway through it. Short circuit evaluation also works for OR statements. If A is true, there is no reason to look at B. So if A is true, it will not evaluate B at all, right? Because with an OR statement, if either side is true, the answer is going to be true. And so once you know that A is true, there's no reason to evaluate B. The answer is going to be true. And so it will skip over B as well. Okay. And that's why when you convert it to assembly, you will get things like this, where there's actually two different comparisons, and it will short circuit. If X was 0, it jumps over the rest of it. It doesn't even do it. Okay. So if you want to have more complicated things, you can do things like write, you can write a 1 into a register and be like, okay, this part of the if statement is true, so you write a 1 into it. Things like that. And syntax highlighting is all off now. I don't even know what's happening anymore. Why is... I don't know what's happening with the syntax highlighting. It's all screwed up. Okay. So your next homework assignment is going to be... All right. So you will be given this unholy if statement in C, and you have to write it in assembly. Oh, we didn't talk about move not either. Move not R0 R0 X is equal to the bit twiddling of X. So what this means is take every bit in 1 and turn it into its opposite. So every 1 that was in X is now a 0. Every 0 that was in the original X is now 1. Shoot, I said move. Move not. Okay. So move not is actually it's not a suffix, it's just a command. It's called move not. And so is move not Shakespeare code? That's funny. Yeah. So what that does is it'll move all the bits from the original, it'll reverse the polarity of the main deflector dish. All the trues become falses, all the falses become trues. And so that'll do that. Tilde in C++ means a bit twiddle. So flip the switch, right? If the light switches up, it's now down. If it was down, it's now up. So you go through all 32 bits and turn all the 1s into 0s and turn all the 0s into 1s. Okay, so for this assignment, you are given an unholy if statement, and you have to write an assembly. That's it. So you have to be correct, as always. In all of my classes, I grade based on correctness. I don't, to a certain extent, I don't care how you solve a problem. I just care that you get it right, because that's, that's the main thing in computer science is correctness, right? Making sure your code is correct. To a certain extent, I care if your code is like ugly or something, but I don't grade you down on it. So, the second thing is fast execution speed. Then there is style for extra credit. So let's see. So for this one, it is code golfed, but rather than our sort of hypothetical cycle calculation from before, what you do is it will actually the code will actually benchmark your code. So we're actually getting into real life rather than hypothetical counting. You know, how many assembly instructions you have. You run it, and it's like it took 73 milliseconds to do your code. Okay. So, yeah. So it runs your code 10 million times. Yeah. Runs your code 10 million times and sees how fast it takes to run. And so par for the course is 73 milliseconds, 108 milliseconds, 83, 95, 44, 80, 44, 83, 44, 105, 44. So it looks like 44 is my best time. So run it a bunch of times, take your best time. That's your result. So par for the course is 44. Okay. And so it is calling that unholy if statement 10 million times and doing it all in 44 milliseconds. That's your. Can you cheat and run it on your own machine? No, it must run on the Raspberry Pi, my Raspberry Pi. That way, it's apples to apples comparison. Okay. And you are welcome to. I think there's a make file. Yeah. So you're welcome to play with the optimizer settings. It's already set on 03. I was just checking to make sure that I didn't do something tricky. I think 1 year I didn't like my students. No, I'm kidding. I forgot, and I didn't have the optimizer turned on there, and so the students were getting these like really poor run times, and that was because the optimizer wasn't turned on at all, and so the C code was not very fast, right? So yeah, the optimizer is turned on. You're welcome to play with the compiler settings though if you'd like. Don't change main.c. You know, not main.cc. Don't change main.c. Like the answer is 0 milliseconds down. Leave Brittany alone. Okay, leave Brittany alone. Don't touch main.c. Okay. So this code will test your code. It'll see if your code matches my code. It generates a bunch of answers for different numbers. It generates 10 million different answers, and then it checks them. And then it tells you how long your code took to run. Okay. So this is the reference implementation here. It runs the reference implementation, then it starts the stopwatch, and it compares your answer against the reference implementation. So this comparison here actually is probably slowing it down to a certain extent, right? Because it's reading 10 million integers out of RAM, and that's 40 megs, so it'll be out of cache, right? So there's definitely some cache misses going on here. So don't worry if you can't get it down to 0, right? What's interesting, .cc and .cpp, there is no difference. So the C language has a standard file extension, which is .c. C++, when it originally came on the scene, a lot of people used .C. The trouble is that DOS, which is what Windows 95 was, Windows 95 was just kind of a thin layer sitting on top of Microsoft DOS, didn't have cases in its file names. So Microsoft DOS did not have cases. You couldn't have an uppercase or a lowercase and be different. Also, every file in Microsoft DOS was supposed to be 3 letters. And so they started using CPP because it's 3 letters, it's all lowercase, and that was how you distinguished yourself between a C file and a C++ file. And for header files, .h and .hpp. You might be like, but wait, we use .h for C++ also. Yes, we do. Does that cause problems? Yes, it does, sometimes. And so sometimes you have to clue your compiler in that this is a C++ header and not a C header. So some people do use HPP just to help the compiler out and be like, yeah, this is a C++ header file. When did they get to 3 letters in C? I don't know if they did, but they still just use main.c, I think. I don't know. Yeah, I don't know. So the other options are CXX. That was a thing. And .cc is the thing also. So I'm a Unix guy. I don't care about the MS-DOS file format system. I don't like capital C because, for one thing, it looks kind of like a lowercase c, especially like when you're like in a file browser or something like that. You have to like, kind of parrot it to see if it's a lowercase. You got like 50,000 files on a screen. You're like, is that a C++ file or C++? So I use .cc. It's one less letter. And given how many times I've typed .cc over the years, it's also probably faster than a Shift-C. You can do CC faster than Shift-C, I think. So it's probably a little bit faster. It's probably saved years of my life. Okay. What language is Windows 10? I'm pretty sure it's C++, I think. Main.ccccc. That's the Clovis Community College, right? There you go. That's the Clovis Community College Center. There you go. The Clovis Community College Center Cthulhu's. There you go. That was the mascot I was pushing for the Chupacabras, actually. I was pushing for us to be the Chupacabras rather than the Crush. Crush makes no sense to me. Crush is a verb. It's not a noun. You can't have a crush. You can't be a crush. It's a verb. It's like we're the Clovis Community College run. Right. We're the Clovis Community College jump. That was a jump. That's a verb. Like, you can't be a jump. I guess you can be a walker, right? Because we got walker in this class. But she's your crush. Oh, yeah, that's true. Never thought of that before. So if we're the crush, that means people has a crush on us. Interesting. Oh my, yeah. But our crush is a bull, so I'm not even sure what anything means anymore. FCC is crushing on CCC. Yeah, but in a different meaning, maybe. Most of the Windows kernel is written in C. Okay. Why is our logo the bull? Because bulls crush things, I guess. They crush cans. I don't know. I don't get her logo at all. Yeah. Okay. Anyway, so that's your homework assignment. Let me go ahead and deploy that to you guys. See if there's anything else we need to go over. Write code here. Okay. Yeah, I just give you an empty function. Okay. Yeah, I thought we should be the Chupacabras. It's a nod to, we're a Hispanic serving institution. Chupacabra is a, mythical creature from Mexico. I thought that was nice. Chupacabras are something to be feared, which is something that. That's a mascot my school didn't want. Thank you, Edit. Yes. It's something to be feared. They eat goats, like nobody messes with a Chupacabra, like, because they kill goats, and suck their blood. It's a fearsome, mascots are supposed to be scary, like pirates, and the Fighting Irish, right? They're supposed to be scary. The CCC chimpanzees, that's funny. No, see, they'd be mad. Like, people would be mad. Like, chimpanzees aren't supposed to be scary, The sharks, you can't be the sharks. That's promoting a myth about sharks attacking people. See, Chupacabras are not real. Nobody could even be mad about it. You know what I mean? It's perfect. In this day where people get mad about, everything, just be the Chupacabras. Nobody gets mad. Nobody is defending the Chupacabras. You can't be talking smack about the Chupacabras. They're not real. You know what I mean? So, CCC honey badgers. Yeah, but then you lose the consonants effect, right? The blood of goats. Yeah. Or the Cthulhu's, the Clovis Community College Cthulhu's. That would also be pretty awesome. So when they had a poll for what mascot we would have, I stuffed the ballot box. I had my students all submit Chupacabra as our mascot, and then they threw them out. I don't think they wanted to consider it at all. They just dismissed it out of hand, and on the ballot it was like 3 or 4 very milquetoast, very gentle mascots. The Clovis Community College positive criticisms. the Clovis Community College supportive environments. Go supportive environments. You can do it. And then next on the field, it's the Clovis Community College positive criticisms. Yeah. The Clovis Community College careers. Yeah. Right. Stop the steal. They. All right. So let's take a look at the worksheet. To be fair, I was having my students stuff the ballot box. So it was completely reasonable for them to do that. But I still to this day think that the Chupacabra would be a better mascot. Okay, it's a hill I will die on. Ask some fizzbuzz, caching worksheet. Okay. This is not due yet. Well, okay, let's take a look at it anyway. I don't care. Cache worksheet. All right. And maybe let's see here. Yeah. Maybe we can just do part of it. Let's do part of it. I don't want to give you guys all of the answers. In CSI 41, I showed my answer briefly on the screen, and then students there's the answer. Damn it. Well, who knows if it's right or not. Okay. So the students went back through the stream and paused it on the one frame my program was open, and then the cheat checker picked up 6 people that copied my code out of it. It's kind of funny. Okay. So stores are always a cache hit, right? They're always a cache hit, and in this model we have here, it's 4 cycles. As we saw for the ARM documentation, it's 1 cycle to do a store, maybe, depending. So whatever. Like I said, the numbers that I throw out for you guys aren't real per se. They're just sort of ballpark figures. They kind of give you I want you to develop an intuitive understanding of the relative cost of things. Okay. And obviously caches don't have 10 elements in it, right? And they're not direct mapped. This whole thing is an oversimplification of caching. You're really going to get into caching more as a junior, but cache moves everything around me. Cream, get the money, dollar bills, y'all. But for this class, I just want you to develop sort of an intuitive understanding of caching and why it's important, and why trade-offs like inlining. Why would you not inline something? Well, until you've studied caches, it doesn't make any sense. Just inline everything. Never have any function overhead at all, right? Well, now your executable is going to be 100 megabytes, and it won't even fit into L3 cache, right? So, could you give us the totals of the cycles for each program? I will walk you through the first one. Okay. And, okay, so here we go. So, store. So this should be 12, right? I do believe that is L1 hit. So 12, and then load from 188, cache it. So 4. Load 211, that's a cache hit also, and then load 111, that's a cache, L1 cache. Miss, L2 cache miss, L3 cache hit. And so what did I say the costs were for it? What did I say the costs were? 410.75, okay. 410.75. Okay, 4 for a hit, 10 for a L2 hit, 75 for an L3 hit. Okay, so let's see if I can mark this up. Yeah, whatever. So that's an L1 hit, that's an L1 hit, that's an L1 hit. So that's 12 so far. And then this one is a L3 hit. Because why? Why is it an L3 hit? Well, this guy got put into L1, L2, and L3 cache, right? This guy got put into L1, L2, and L3 cache. This guy got put into L1, L2, and L3 cache, and it overwrote this guy out of L1, and it overwrote this guy out of L2. So this guy is still sitting pretty in L3. This guy has displaced them from L1 and L2. So 4 cycles, 4 cycles, 4 cycles, 75 cycles. So 12 plus 75 is 97. So this is off by 2, I believe. Okay. You guys with me? So even if you guys see the answers for the other ones, don't trust them. Okay. So, all right. 75, 75 plus 12 is 87. 87, yes, sorry. Okay. 87 is the correct answer. See, I didn't want to give you guys the answer. 87 is the answer. Okay, so store 1211. Okay. So 1211 is going to knock 211 out of L1. It'll knock it out of L2. It'll knock it out of L3. Right? Because he's in slot 1 in L1. He's in slot 11 in L2. He's in slot 211 in L3. So 211 has been completely evicted out of the cache. Cool. So that's an L1 hit. Because it's a store. It's an L1 hit. Stores are always L1 hits. So that's 4 cycles. Then we load 211. So 211 is back in RAM. And RAM is... 200 cycles. Oh, we no, we have, yeah. RAM is 200 cycles. Okay. Okay. So L1 hit 4 cycles. That's a RAM hit. So that's, or it's a cache miss. So do you guys see why caching is important? We just were messing with 211 a second ago, and now it's out of cache. And so that's a cache miss. So what's going to happen is that's a 200 cycle penalty there. So 4 cycles, 200 cycles. Now it's back in cache. This guy is back, baby. This guy has been evicted. 1211's been evicted from cache. 211 is back in L1, L2, L3. So cache hit, L1 cache hit, cache miss, L1 cache hit. So that's 208 so far. And then we're loading 1211, who just got evicted. So that is another 200 cycle penalty. So it's cache hit, cache miss, cache hit, cache miss. So the total cost of this is 408. Okay. The total cost of this is 408, not 503. So congratulations on doing it early. You get the professor reviewing your worksheet and correcting you. So that's an L1 cache hit, cache miss, 200 cycles, L1 cache hit. 4 plus 4 is 8. Cache miss is 400 total. So 408 is the answer. Okay. Oh, he's doing a cumulative cost. I see. All right. Yeah. Good. Okay. Store, hit. So 4, 8. And then we're loading 211. That's another cache miss because this guy evicted him from L1, L2, and L3. So that's a RAM 200 cost, and then load 111. 111 is still in L3 cache, so that's an L1 miss, an L2 miss, an L3 hit, because 111 is still in L3. Nobody evicted 111 from anywhere. So that is, let's see, 4, 8, 200, 208, 208 plus 75 is 283. So, right, 8 plus 200 is 208, plus 75 is 283. So very close, but off by 3 somehow. I don't know how you got a 5 in there. 75. I don't know. Okay, so yeah, so the total cost of this is 283. This section is 283. And I guess you can write it cumulatively like this. I would just write, unless I said otherwise. Say otherwise? Yeah, I mean, I would just write what the cost is for that section. Okay. So I would just write what the little sections cost is personally. You can do it cumulatively, and I'll figure it out, but it just seems like a waste. Okay. Any questions about caching? Okay. Can you just write a program to calculate it for you? Sure. Yeah. I mean, that's actually something we might do in this class, is actually a cache simulator. Thought about it. Using bridges. We can visualize the cache on bridges. It'll be fun. Do it all in assembly. Have assembly call bridges. Yeah, it'll be fun. I haven't taught you guys how to call C++ code yet, so don't worry about it. For now, ask them if, due next Tuesday. Have a good time, guys. Peace out. If you have any questions about the caching, just send me a message on Discord. Okay? See you. Thank you for class.